Now we're going to concern ourselves with collisions between objects. Here I'm imagining two blocks. Maybe they're in outer space and they're on a collision course, or maybe they're on a frictionless track and they're on a collision course, or maybe they're just sliding across the table toward each other. And so we'll call them mass 1 and mass 2. I've colored them different colors just so that we can easily distinguish them. And they might have different initial velocities as well, but they're on a collision course. So here's the before picture. And afterwards, we're going to imagine that perhaps they go in different directions. If M1 happened to be really massive and M2 were really light, like a ping pong ball and a bowling ball, then they both end up going in the same direction afterwards. But they have some final velocities, so we'll call the initial velocities V1 initial and V2 initial, final V1 final and V2 final. And one thing that we know for sure about the forces that are acting between these two when they're actually in contact with each other, we're going to assume that they make some sort of very quick collision that only takes a very short amount of time. And at every instant of time during the collision, the force of 1 on 2 has to be equal and opposite to the force of 2 on 1. That's just Newton's third law. If we then assign an x-axis to be some direction along the direction of that one of them is traveling, then certainly the same thing is true of the x components of the force. And in this case, our forces as pictured would only have non-zero x components. What we can now do is we want to relate this to impulse, and so we can multiply each side by the time interval that it takes that they're in the collision. I'm assuming delta t is really small, and so then we can re-express this as the force of 1 on 2 times delta t's x component is nothing but the impulse that 1 imparts to 2 x component, and the force of 2 on 1's x component times delta t is the impulse that 2 imparts to 1 x component. So that relates those two impulses with the same minus sign. Now we're going to assume that those collision forces that we're talking about up here, the contact forces between the two things, are the only forces that impart significant impulses to each body during that very short amount of time. In other words, we're going to apply the impulse approximation and say, hey, maybe these things were sliding on the table, so mass M1 also had a friction force on it while it was colliding with mass M2, but the friction force is not going to apply or impart a significant impulse to M1 compared to the huge impulse imparted by M2 on M1. That's the impulse approximation. So we're going to say, look, the net impulse on 2 is essentially just the same thing as the impulse of 1's contact force on 2. And same thing for 2 on 1. That's the same thing as the net impulse on 1. Now we'll apply the impulse momentum theorem because, in order to apply that, we have to concern ourselves with the net impulse being delivered to some object, and that's equal to the change in momentum of the object. So in this case, the change in momentum of object 2's x component is equal to the opposite of the change in momentum of object 1's x component. Now let's rearrange this relationship. We're going to write delta as final minus initial, so that's all I've done there on both sides. We can distribute the minus sign over the parentheses, and then we're going to put all the final stuff on one side. Here I've put final on the left-hand side, and everything that has to do with the initial state we put on the right-hand side, mixing up the 1's and the 2's. And so this says that the sum of the initial momentum x components of object 1 and 2 is equal to the sum of the final momentum x components of objects 1 and 2. And that is part of the statement of the conservation of momentum. Here we've only done it with x components, but we could have had something colliding in some way where they weren't colliding head-on, and maybe they moved along the x and the y and the z direction during the collision. The statement of the conservation of momentum for objects colliding maybe in multiple dimensions is that the total initial momentum, here I put that on the right-hand side, total initial momentum is equal to the total final momentum. That means the sum of all the momenta of the objects in the final state equals the sum in the initial state. That's the statement of conservation of momentum for two colliding objects. It assumes the impulse approximation applies. And here, if we're applying the impulse approximation, we want to make sure that initial means just before they contact each other, and final means just after, and we're assuming some sort of very quick collision. So here's a more general statement of it. We could perhaps not just have two colliding objects, but maybe we have 10 different objects that are all colliding with each other, like billiard balls on a pool table or a bunch of rocks colliding in outer space or something like that. And the statement of the conservation of momentum, which applies in both collisions and also, a bunch of items could come together and stick together, or maybe a single object could explode into multiple pieces. This applies to all three of those kind of cases. As long as the impulse approximation applies, in other words, we have a very quick collision and the other forces that are non-contact forces between different objects don't impart significant impulses to the objects, then the total initial momentum equals the total final momentum. We call that conservation of momentum because conservation means something doesn't change over time. In this case, the total momentum doesn't change. So this applies to a bunch of objects colliding and then going away from each other, or maybe they all collide and stick together, or maybe they were stuck together in the initial state and they explode apart into a bunch of pieces. All of those have to do with the conservation of momentum. And I should mention on this previous slide, sometimes people also state the conservation of momentum in terms of the changes, although this is only going to make sense if there's two objects colliding. We could say the change in the momentum of one object is equal and opposite to the change in the momentum of the other object. That's another statement of the conservation of momentum for two colliding objects. Okay, so sometimes people just say the total initial momentum equals the total final momentum. That's conservation of momentum. Okay, let's go to a worksheet problem and then we'll take a break. Here's a 3 kilogram hockey puck moving at 3 meters per second in the plus x direction, collides with a 12 kilogram curling stone. My apologies to you if you're into curling or hockey because I just made up the masses of both of these things. The curling stone's initially sitting at rest, and for some reason the two stick together. So maybe they're covered in Velcro and the puck sticks to the curling stone. And the two move as a unit in the final state. What's the velocity x component of the puck afterwards? And in this case, that's question A. You should also try to complete question B1 and come back and you'll see my solution.